Okay, example 3. In this example, and we know the EI, this is 12 by 10 to the 7th kips inch square is a constant, and determine the following parameters. The deflection and slope at the point B in beam 1. And here we have two beams, two cantilevers actually. Here is beam 1, and here is the beam 2. Okay, you're determining deflection and slope at the point B of beam 1, beam 2, and deflection and slope at the point H of beam 2. Here is the point H. Okay, so first of all, as we did in example 2, we need to convert the unit system to make sure they are consistent. So in this example, we can just use kips and inch. While we use kips and inch, so these known conditions can be converted. The first one would be the M. That is 40 kips feet, while this one equals 40 by 12 kips inch. And the L1 will be 9 feet, that is 9 by 12 inch. And L2, 6 feet, that will be 6 by 12 inch. Then we can start to examine these two beams. And the question number 1. Deflection and slope at the point B of beam 1. Beam 1 is right here. Right, it's not even a combined loading. You have only one cantilever and one concentrated load, that is a bending moment M at the free end. We just turn to the table. And here is the case. Right, so if we want to determine the deflection at the point B, you can just directly use this equation, 26, and for slope, use 25. Right. So just directly use these two equations, we can get the slope at point B is negative ML over EI. That is negative 40 by 12 by 9 by 12 over, and here the L is L1, right, as indicated here. So you get 9 by 12. And the EI is 12 by 10 to 7th. The results will be negative 0.000432 radian. And here we use equation 25. Right, then to determine the deflection at the point B, we just calculate it directly from equation 26. Right? That is a negative M L1 square over 2 EI. That is negative 40 by 12 by 9 by 12 square over 2 times 12 by 10 to the 7th. And the result here will be negative 0.02332 inch. And this is our equation 26. In the second question, deflection of slope and the deflection of slope at the point B of beam 2. We look at beam 2. The beam 2 is right here. right? So if you add a concentrated load, concentrated bending moment M to point B, this is actually the same as the first beam, apart from you added another section, BH, to it. So this will not change anything, right? This will not change anything regarding point B. So it's theta B will still be negative 0.000432 radian, and its delta B will still be negative 0.02332 inch. This will not be changed. Then how about the point H? Right, the point H is right here. So based on the loading, if you draw the bending moment diagram, you will get this. It has a, this should be a positive or negative bending moment? Well, is this bending moment M positive or negative? Well, do you remember our golden rule? Right? If it makes this cantilever or beam cry, it will be negative, right? This, according to the direction, it will make it cry. So this is a negative bending moment. So the bending moment diagram will be a negative constant value M from A to B. Then is there anything here? Oh, no. No bending moment at all on this beam section BH. So it's nothing on it. That means this section BH will not be bended. It will not be bended. So after you add this bending moment M, this section BH, section AB will be bended in this way, and the BH will keep a straight line here. Okay, this BH will still be straight line section, and so you can calculate the slope, that is the angle, theta B or theta 2 as shown here. Right, but this value will be the same at this point, at a point H. So since they will have the same tangent direction at point H and point B, tangent direction is the same. So here, the theta H will be the same as theta B. Right, so your theta H equals theta B equals negative 0.000432 radian. Then how about delta H, the deflection at point H? So here, this deflection at point H can be split into two parts, and the first part here, delta H1, actually the same as delta B, right? And you have the second component, delta H2, from here to here. This deflection can actually be determined based on a triangle, right? Based on this triangle. Then this one can be split into two components, equals delta H1 plus delta H2. And this equals delta B plus something. Well, this something here is actually, you can determine it based on a triangle. And let me draw this triangle. The triangle is here. Right? So in this triangle, this delta H2 can be calculated from L2. Here is L2, right? After the rotation, right, it will be L2. L2 by sine theta B. right? So here we will get L2 by sine theta b. And this will be negative 0.02332 minus L2 to the 6 by 12 by sine 0.000432. Okay, and here you will get negative 0.0544 inch. Okay. Here is the final solution of the deflection at point H in beam 2.